Hey, welcome everyone to class 6 of SQL 101, Data Manipulation and Management. I am Jeremy Bergman, the instructor for this class in Omaha Data Science Academy. And tonight we're going to learn about structuring and modeling data. So how do you design these relational database systems to be able to capture transactions or the analytical data that you need to be able to accomplish your goals within a system or answer those questions that drive business results or help improve business, hence the name business intelligence. And then modeling data. So how do you design the table structures or the relationship structures to be able to handle this type of relationship? So we'll see that there are a couple of different methods of doing it. Oftentimes a data analyst, they won't often have their job as creating a new database management system or relational database and tables and things like that. But as we've seen through class, there may be a little bit of it. Plus, if you have these documents wherever you go in business, it's really useful to be able to identify them and understand them and understand the relationships in the database or how the database is built for those like system processes, how it captures data and the relationships between the tables. It can tell you a lot about how the data is stored and produced in those business processes too. And then also some of the modeling data, we'll cover how to model it for analytical purposes. So whenever we've talked a lot about data, capturing it from transactional systems, oftentimes that's not in the type of format that you need for analysis. We talked about that a little bit in the classes, especially when we talked about creating views. And then the last class is a really practical one as far as cleaning data using SQL. That's like for analysis purposes too, oftentimes. And reporting. But we'll also learn how to model data for analytical purposes, taking that transactional data and modeling it for your analysis and what that looks like. Okay. So how is this class structured? So the first hour, I'm going to provide an overview of database modeling and brief introduction into online transaction processing. So online transaction processing, that is capturing transactional data from systems and how you capture those requirements and design those databases. So there are a few different techniques that you can use to do that. Cover that in the first hour. The second hour, I'll cover online analytical processing data models. So online analytical processing, don't get too confused about the term. It's just taking that transactional data and using it for analytical purposes, the way analysts would use them. And there are a couple of different data models you can create. And then last, we'll talk about normal forms, which go across both online transaction processing and online analytical processing, relational databases, and data models. Then in the third hour, we'll do an exercise, OLTP data modeling using ER and relational diagrams. And if I can, we'll also do an example of online analytical processing with the SQL database. Okay. But just a high-level review of class 2 to 5, I was telling Celeste right before this class is basically you've learned all of the basic SQL that you need as a data analyst. So being able to create new data sets and combine disparate data sets, you learn that through the first 4 lectures with just being able to query data, creating a new data set or result set. And combining data, you learn that in class 4, being able to join tables together by some key. So you can really create a lot of new data sets and extract that data out of those tables the way you need using the SQL programming language. Performing common queries, aggregation, and joins, so transforming the data the way you need it as a data analyst for analysis. Adding, removing, and modifying data, so manipulating data, so creating databases and tables to be able to store data in the way that you need to be able to store it. And then also, once it exists in the tables, being able to add to it by inserts, removing it through deletes, or updating the data. And then last, storing and maintaining data. So you also learn that through updates, inserts, and deletes. And so one of the big benefits is the persistence of data in relational databases. So once you store it, it's there, and then you can update and insert it as the data. You can change the profile as the data changes within the table data profile. So we've learned all of those basic skills. So the last two classes are going to be over database modeling. So how do you design these databases to capture transactional or analytical data? There are a number of different types of models and techniques you can do for this. We're going to discuss OLTP versus OLAP modeling. So capturing transactions versus analytical data. And I introduced, or on the first slide in the introduction, talked about that. Go in more depth. Normal forms. So there are a lot of different normal forms in database theory. We're going to cover the first and second, because first normal form is just like the basics of relational databases and how you want to structure a table with a primary key. And then the second normal form is how can you simplify that table even further? How can you break it down even further? So maybe one table becomes 2 or 3 tables that are easier to maintain and update and manage. Analytical processing, we'll cover that in the second hour. There's a thing called dimensional data modeling, especially useful for capturing data over time and summarizing data and putting business rules the way you need it for whether it's reports or dashboards and so forth. So making you aware of what analytical processing is, and then how you would maybe design and then read an existing dimensional data model. So data models, if you've ever heard of the term data warehouse, maybe you have or maybe you haven't, they often contain dimensional data models for analysts to use. So being able to read the diagrams in one of those designs, I think, is an important skill. And then we'll do an example with database modeling on the Sequila database to bring all this together tonight. Okay. So the purpose of database modeling. So database modeling is like creating a blueprint for a complex structure. It gives the construction of robust databases and efficient information systems. So think of it as like the blueprint for building a house. It can be pretty complicated as far as, you know, where all the plumbing, electricity is run, how the structure is built, the roof. Think of it as like the blueprint, a couple of different types of blueprints to be able to build a house, all the way from like the highest level, like just some type of drawn out design of the rooms, to like the details of how the plumbing and electricity is run. And do the same type of work with databases. You can do the same type of planning with databases. So some of the benefits, it illustrates data relationships and structures. Being able to have those in a diagram versus just guessing at them is huge. In my experience, not that many systems actually have very good documentation like that, but when you get it, it's a huge help. And especially in enterprises, they generally have those type of diagrams just by the nature of being a little bit better about policies and procedures and documentation. They help requirements clarification. So This is a role of like an IT business analyst to go out to business users and understand what they need from the system. These diagrams will help them and the user be able to like create the right design or like understand the relationships that need to be there within a relational database to be able to meet what the business users need to do. Very important to be on the same page, and it provides like some of that blueprint. Think of like someone trying to build a house, like what are their requirements? What different rooms do they want? How many bathrooms, how many bedrooms, so forth. This does the exact same thing. It's like the technical, one of the ways technical people communicate with the non-technical people and get exactly what they need. Quality assurance. So modeling a database helps with integrity, consistency, redundancy of data so that you can design a database in a way that's efficient and make sure that you aren't overwriting a bunch of values in the database and that it's consistent across the database or redundant data. It's really to make it more efficient, and then with data governance, enforcing standards for data capture. So this actually still doesn't happen a lot. Data quality assurance and data governance. A lot of these systems are kind of built ad hoc as they go. But when it does happen and people are thinking about it, when you do database modeling, it helps those efforts out a lot. Say performance optimization, creating the most efficient database that you can for either capturing transactional data from a system or for analytical purposes and requirements for like reports and dashboards and so forth. Consistency and predictability, so you know exactly what processes you're capturing from the system and data behind it. And then, of course, supports business processes also, which goes along with all of these, but making sure you design a database that supports the needs of people's processes and the things they do within their job function or the enterprise in general. So I have this diagram. I talk about data model that supports the systems and data produced, whether it's transactional or analytical. It helps support data integration between systems, simple interfaces that are built. So within a system, imagine like inventory management system. You're entering new inventory. You're designing a table, maybe an inventory data that connects to that interface. Then a user will enter some information on a new product or update an existing product. That'll just go right into a database table behind the scenes that you design. Minimum redundancy of data and compatible data. We talked about that with quality assurance and data governance. So designing a database that's as efficient as possible and has business rules and the right data being captured. And then these systems support your business, really. So being able to do the things that you need to do, identifying business opportunities, being responsive to change. Hopefully your systems aren't built in a way that it becomes a lumbering giant. That's why database modeling helps. And that way you reduce risks and reduce costs. So all of this is in support of your business objectives, whether you're doing it for a transactional system or for analytical purposes. All right. So we talk about database modeling. What type of database models are there? This mostly does apply for both transactional data models and analytical data models. So it goes from highest level view, the most abstract or the with the highest abstraction. So you don't have to be really technical to understand the conceptual model, which is why it's a good tool to kind of diagram with business users, like the relationships that they need to be able to capture the data that they need from their business processes. Then there's a logical model. So this will start to look more like the work that we've done in this class. So you're taking this conceptual model and you're turning it into tables and relationships with primary keys and fields. And then the physical model is exactly what we've been doing in this class. So you're starting to create the table, you do the different data types, create primary keys, foreign keys, and so forth. So we haven't covered it a lot. So the foreign key is, it's not a key of this table's orders, but it relates to a primary key of another table. So think of an order. It has an order ID and then a customer ID.
So each table has a primary key?
Yep.
And only one primary key?
Yes.
Okay. And then so in relation of one table to another, like if it's somebody else's primary key, it's called a foreign key?
Yep. So it's not the primary key of this table. So think of orders. Like you have all the order IDs 1 through 1,000,000 or how many of our order IDs there are. That's a unique key for that table. So customer ID isn't, but you'd have customer information within the orders. So you could connect the customer table to the orders and be able to see what customers are related to which orders. But then it is the primary key of the customers table.
Well, like if you're just talking about like tables, like related
Yep.
to each other, like, can you describe it?
So it's not the primary key of orders because that's order ID,
Okay.
but it is the primary key of the customers table, which you can relate to the orders table. So it's basically customer ID is a primary key of another table. And so it's a foreign key of the orders table.
Oh, okay.
And we'll see more of that here. I started to put it in one of the homeworks, but we hadn't learned about foreign keys. We just learned about primary keys. But we'll learn more about it here in the database design. So yeah, we have logical and physical models. The conceptual model shows entities and their relationships. So entities are like customers, orders, and products. Those are like nouns within the business, your requirements. And just focuses on the business concept or process rather than the implementation details. You're just trying to capture this all down on paper, the types of things that people are talking about and the entities that are involved. So think about a process that involves a customer and an order and a product. Maybe they're ordering off Amazon. Maybe you're ordering off Amazon. You as a customer is creating an order for any number of products. And then you define those relationships. So it'd be one order to any number of customers to an order and any number of orders to a product. So then you start to define the relationships and what they call the cardinality of the relationships. So is it a direct one-to-one relationship where one record matches exactly one on every table? Or is it where one order matches any number of customers? Or many orders can match many products? So that's especially that one's easy to think of. So you have a whole bunch of orders in the table and they could, there could be like 1,000 orders that are related to any number of products. All right. So logical model is a step down with that. From that, once you capture this conceptual model, you start to turn that into like the nouns and then the adjectives. that describe the customer and that things that describe an order. And then in the relationships are like a verb, and we'll see that in a second. So it becomes very natural to be able to transition these type of models into your logical and physical models. So this is where you start to talk about like all the attributes within these entities, these tables. So what do you need to capture about each customer, like their customer ID, name, and email? This is just a simple example, but you can imagine all the different things you'd capture about a customer, like phone number, address, any amount of contact information, or just information about that customer itself in relationship to the business, like are they a preferred customer, be yes or no. It's more detailed, so this type of model is more detailed, obviously. It includes entities, attributes, and relationships. We covered that. These are the entities, the nouns. The attributes are the fields, or what describes the nouns. And then the relationships between them. So customer is connected to customer ID in the order table. And once you have that, then you can design your physical model. And this is what we did in lecture 3 with the data definition language, like creating tables to capture the data. So you create these tables, you have all those fields, and now we're defining the right data types for each one of those fields. So that can be important, like you say how long is the longest name that you're going to need to capture, or the longest email, or should these fields be an integer or decimal, or should we do date times and date stamps and that thing, and then how they're all related together. So this physical model is often where the analyst will start working with like a database administrator to be able to come up with the best physical design possible. Logical models here, they should be independent of the database that you're using. So no specific relational database. And it's a type of planning that you do before this physical implementation, which uses actual SQL statements. Often it's specific to a database management system like MySQL or SQL Server. And like I said, this is like where the tech guys hang out right here. You take the requirements, the business analyst, maybe the data analyst also. Oftentimes the data analyst might be involved. And then you create this into the best implementation possible. That's how the most effective database models are created for systems, whether transaction or even analytically. Okay, so we're going to talk about that, the difference between transactional and analytical processing. So 2 very different purposes, like I've described. OLTP is capturing operating processes and data like order processing, inventory management, or customer support. Ideal for making simple updates, insertions, deletions into databases. That's like what these transactional systems are doing. They're doing this really fast. They're optimizing for that, like hundreds of new transactions or updates to records, or even deleting records for whatever reason, deleting history, purging data, and managing data that's coming from a transactional system. How do you design that in the best way possible? So analytical processing is for different purposes. This is for complex analysis and queries, data mining, forecasting, using pre-existing business rules. So OLAP is most common like use case, or the reason why you do it is to capture analytical data over time. So you have like oftentimes you'll have a number of snapshots in time of the system, and those may be lost in the system for all these transactions being overrode, but you're capturing them for analytical purposes. So you can go back to it and revisit it and summarize it and do complex analysis in a bunch of different ways. And that is like the definition of why you'd have a data warehouse, is to take that type of information and then convert it into what you need. Your analyst needs to drive business decisions. So you say pre-existing business rules. Oftentimes these business rules come from the system, like certain things, like I'll create something silly out of my head because it's usually how my brain works, is that maybe on Wednesdays there's half off some item. And maybe that's not really that silly, but you imagine that and then capturing that within a data warehouse. So you would say on every Wednesday you create maybe a view that says every Wednesday we run this promotion. And then you can go back and retrospectively analyze that and see how it does. So you capture some of those, and then usually it's some other business rules too that are meaningful to the sales teams or marketing teams and so forth that you integrate into this. This really becomes its own effort to take, I always call it turning data into information. This is taking all that data that's being produced and turning it into information that drives business results, which is what data analysis and business intelligence is all about. Right? So key point is that these should also be separate, because OLTP systems are generating all of these transactions and trying to keep up with it with only finite computing resources. And it shouldn't be bottlenecked by analytical functions. And this allows day-to-day operations to be unaffected by analysts and stakeholders. I include this because this has happened a number of times to me as an analyst, is that go in and query a transactional system during the day, and the team screams at me for slowing down the system, or they're like, it's that analyst again. He's causing all the problems with our data and locking our databases and so forth. And there's really nothing worse that you can do as a data analyst than disrupting a production system, because then people can't do their jobs and that's money lost, and you'll feel horrible. You'll feel horrible from it. So I've been there a couple times. Ideally, you would just extract data and take a snapshot of it, and then turn that into the analytical data that you need. And through an analytical data model, or even sometimes it's just a snapshot until you get to that point for the analyst to use it, so it's not disrupting the system. So decoupling these improves overall performance, scalability, and consistency of data for both of these, actually, for transaction processing, and then really transforming it into the analytical data that you need, which it's not always that way in the transactional systems. Oftentimes it's not the way you need. Okay. So there are a few different techniques involved here that you can use. We covered these really with mostly with the types of database models, but we have the entity relationship diagrams, the logical model that displays entities and basic relationships, the tables, and the relationships between them. You have relational modeling, so it's a physical model that we saw, that was the in-between, where each table is an entity with fields that are like properties and relationships. One of them we did not cover is data flow modeling. So this is a data flow diagram. Understanding this is really important as a data analyst, because then you start to understand how data is generated by different actors or different users of the system, and then how data and information is relevant to them. So imagine like a sales team, like they want to know what customers are ordering what products from what supplier. So you can see the processes that the customer goes and confirms order details, connects to like maybe a parts table and a supplier table, and then bringing that all together so that that data is relevant. It turns into information for the sales team or the marketing team or whoever it may be. So understanding how the data is generated is a key into turning that data into information. Data flow diagram can help with that. Helps with gathering requirements for the transactional system. It also helps a data analyst understand how data progresses through multiple systems and multiple processes in each input and output to turn that data into information for the relevant stakeholder. Then dimensional modeling, just talked about that. So, but this we'll talk about in a little more detail. So that's taking that transaction information, turning it into analytical information. This is a physical model set in between where data is organized into facts. So facts are like things that you could sum up. You could sum sales, revenue, number of customers, and so forth. And then dimensions often include some of your business rules or information about stuff like product or locations or store information or brand or vendor or any number of dimensions about your business. You see this if you use Tableau, you'll see, actually bring this up, things in dimensions and measures, which is exactly this concept for analytical modeling. Tableau uses it itself. So a project that I've recently worked on, these would be these things in your blue. They're like your measure, your dimensions, like codes, dealers, file names, and so forth. And then these are your facts. So like your estimated hours for some job on an invoice, some task on an invoice, or how many hours they punched versus how many they invoiced and how much was the total dollar amount. So it becomes a very natural way of analyzing data. And then you could say, what's a good example in here? You could say what dealer, you could answer questions very fast. So what dealer has the highest number of part sales for a given part type or job type or so forth. So you're taking it in dimensions and facts and organizing it in a way that becomes very fast and efficient for answering those business questions. Plus, the data doesn't always exist permanently in those transactional systems, so it's a way to capture that information for future analytical use. So that's actually a lot for the first hour that we covered. How about we take a break we'll take a 15-minute break, and we'll cover both the details of OLTP modeling, analytical modeling, and the normal forms before we get into the final hour. Seems like a good stopping point before we dive deeper into each type of database modeling. So we'll do that, take 15 minutes, come back at 7:20. Then we'll do all of this. We'll get to our example in the final hour. All right. Let everyone grab a snack, drink, and hold on tight for the rest of the lecture. But I feel very valuable on how these things are designed and thinking about data. Well, there's transactional systems, and then how you take that and use that as being able to look at these diagrams and saying, how do I use that? This type of diagram right here. It's a Sequila database, but how do I take that and understand the tables and the processes and turn that data into information? So 15 minutes, start again at 7:20. See you in a few. turn the volume back on as I'm talking to Celeste. She is talking about seeing these type of diagrams with Microsoft Access in the past. And we'll do an exercise. Part of the exercise is doing that in MySQL Workbench with the Sequela database. So a lot of times there are tools built into the database that allow you to visualize the database. Not always either, but there are also tools that you can sometimes pay for that will kind of reverse engineer the database for you. You'll go through it and figure out the relationships. But you run into the problem sometimes of it being a production database, so you have to do it like 10 o'clock at night when everybody's off of it and nobody's really that helpful. So you end up just kind of figuring it out yourself. Usually I take it offline, like I was saying, it's like just select all from the table and save it as a CSV file so you can load it up in Tableau or load it up into your own database tables and look at it that way. And then transform it the way you need to. Usually I'll just take a copy of the entire thing and export it. And that's usually what I ask clients to do. If they have a bunch of data in their transactional database and they don't want me to touch it, I just tell them to give me everything that you have in CSV files. And then we learned at the beginning of class, you can import CSV files through like the import utility. That's really slow though. And oftentimes it errors out. That's why Tableau is one of my best friends, is that you can easily connect the Tableau to the CSV file. Connect it to a text file and then just load a big file up. That one's a big one, 200 megabytes. And then just say I'm okay with that, and then just start dropping the dimensions and measures as analytical data, and then build in all your rules through calculations. You can create your calculated fields and things like that. So really, Tableau is like an OLAP data analysis tool and dashboarding tool. And so is Power BI and things like that. But I can do that and do some of my data analysis in here, figure out what I need. And as part of the final project, hopefully you can use either Tableau or Power BI or something to connect to your database tables and do the same. That's the goal. But I'm trying to get it right. So have the homework by Wednesday for the final process. Homework over the last few lectures to get to where you need. And oftentimes you aren't doing this step at the end. You're doing it more at the beginning.
Yeah.
Or close to the beginning when you're analyzing data and trying to understand it. But it's really a feedback loop. It goes back and forth.
Yeah.
I did that, talked about that.
But that's really exciting that you got your MBA, though, and so that you really can look at everything in a new way.
Yeah, it connects me with business management. I felt like I was already, but oftentimes they'd say, oh, he's a technical guy. He doesn't know what our needs are. I came across that a lot as a consultant.
saying the right words.
Yeah, it's like speaking their language, right?
Exactly.
I don't have the in my oh no, I have the CRISP PM process. So understanding business problem all the way to testing and evaluating and deploying it by answering business questions. But oftentimes you start to understand the business problem, and then you start to understand the data, and then you're like, ooh, I already need to refine the business problem once you start digging into it. Or you start to prepare the data, and then you decide I need to go back and understand more. You're building your model or data flow. Perhaps that's where you're starting to build like your analytical model or your machine learning model or whatever it might be. You make sure that that process works. Sometimes it doesn't, and then you have to go back to understanding or those steps, and then you deploy it. But this process is never really done, because once you deploy it, you start answering business questions, but you generate other questions from seeing it in a new way. So you're all of a sudden starting back at the beginning. But that's why data analysts are so valuable, is that they can understand systems, they can understand processes, and then connect that with people in business to get the data that they need. And the business people almost can never do that themselves. And a lot of the technical people don't want to. So, where they don't speak that language. So, I've learned a lot from being in that position about systems and business and information that people need, helping them solve their problems. Then making a career of a consultant and a teacher out of it. Okay. Just wanted to bring that up. I might have gone off the rails there, Celeste. You're talking about seeing those diagrams before in Access.
Yeah, I saw them, and so when I see them, it's not the first one I've seen. I tried to understand them when I've seen them, but that's all. I mean, just what I've seen.
Yeah, and then I was talking about oftentimes you do that at the beginning of the process, but it's all iterative.
Yeah.
And that's like the key of being a scientist, is data analyst or data scientist, is be able to take all this information and digest it, and I just hate to say regurgitate it. It's like mama birding it. It is kind of like mama birding it to whoever you need, but
I feel like that's what learning like. Just like learning things.
I feel like I've used that analogy before. It's like that, getting it, processing it to where the end user needs. There's a lot that goes into that. And to me, that's what makes a good data analyst really valuable, even if not everybody appreciates it. Oh, it's underestimated. Like, people don't have no idea, like, everything that goes on under the covers. It's kind of life of being an analyst.
I can see that, because
being a developer.
How long things take. It's a simple question, but it really crazy.
And the business owner will be like, all the data's right there in the system. You just pull it out and answer the question.
Yeah.
You have to use some persuasion skills too to talk to people and help them understand, guide them to the solution that they're looking for. Being a data scientist and a data analyst, I think talked about that at the beginning of class, but you're both technical and non-technical at the same time, which makes you hugely valuable once you develop all those skills. And doing all this, looking at these diagrams underneath the scenes, is taking in, processing all that information, and then connecting the dots between the technical and the business and the processes and the non-technical. All right. Let's go ahead and get this started again.
Sure, that's why I actually like this kind of entering the tech world in this capacity. Because if you do have that kind of view that in between, like not, you do need to be able to discuss things that are non-technical.
Yeah. You get some visibility for it too. So it's not all
and I like
taken for granted or anything like that.
The idea of analyzing data. It's just one of the things that is really fun.
I like solving problems.
Exactly. Yeah.
And by doing all this and using data, it's kind of way you can use all your skills and put it together.
Have you ever found something? What was like the thing that you found that when you were at a job that you found that was like kind of remarkable and interesting thing that you discovered from your work?
One of the most interesting things I did?
Yeah, that you remember.
Early on, I did a fraud project at First National Bank. So it's like this scheme that I won't name any ethnicities, but a certain group in California was running on banks. And they wanted to try to be predictive about it. So they were looking at predictive factors for this thing to happen. So basically, like, what people will do is get near their credit limit and then make a huge purchase. So they go way over the limit. And then they won't have the funds in their bank account to pay for it. And then they charge off their credit card. So they're trying to find things that were predictive, but the challenge is that you can't racially profile anybody in banking or stuff. So you have to try to figure out behaviors that are non-related to ethnicity or gender and stuff like that, or income.
Is it zip codes? Is that?
Can't do it at the zip code level. It says too much about the target demographic. So we did more or less find some criteria that was about 50% predictive. It's kind of a small target, so you end up with like a lot of false alarms if you go too crazy with it. But a way to put the transaction on hold before it happens. And basically they came up with, there are a couple of rules, but I mean, sometimes it comes up with a simple answer, just like not letting somebody go like over 130% of their credit limit or something like that. Like for all of those transactions,
would they have like opened the account, like having gotten to that position like within a year probably?
Yeah. So they had it for a little while. It's almost exactly 15 months. They have it a little more over a year, and then they had a credit limit. They raised their credit limit before they did it. So there's some semi-predictive factors. Yeah. They had an amount of credit history. But then you make a couple decisions after finding that, right? That's what the end of this project's going to be, is you decide that certain actions are good actions instead of just cutting, what do they say? Cut off your hand to spite your face. I don't know if that's the right one, but cutting off a whole bunch of people.
Yeah, when you talk about like
like using data to do it.
When you talk about overanalyzing, being like a potential danger and so that's like, I think that when I played with databases, I really don't remember any of it, but that would be what I was doing.
Yeah. All right, we'll jump into this OLTP modeling. We have a bit more to cover today. Okay. So the first hour is learning about all these techniques, the difference between OLTP and OLAP modeling and different types of database models. So we're going to dive deeper on online transaction processing, database modeling. So focuses the operation of a particular system. Goal is to design a database that captures those events. All right, so the model maps how information is stored and relates to other data. So this is really like the different types of models that you'd have. You get data requirements in your activity model, turn it into logical conceptual models. You'd update that in your technical environment. Your technical team would start to get involved in the physical data model, and then you create this with process and update it with business data captured from your processes. So this type of models map how information is stored and relates to other data. ER diagrams are a formal mapping process. That's to help you gather requirements up here to create your logical models. And then a map of the database schema, which is when you start to get to the physical model that we saw when you're creating the second step, your entities, attributes, and relationships. And then your physical model, which is like your SQL implementation. Okay. So data flow modeling, briefly touched on this, but it describes the flow of data through a system or process, and it models the process interactions. So processes performed on data, where data is stored and it held, like customer carriers, sales orders, credit cards, and then the people and systems that interact with that data. So like your customers, your carriers, maybe some of these would be people working in your shipping department and so forth. It's useful identifying areas of inefficiency or design and communicate system requirements. So this is what's kind of designed to considered another high-level diagram, and making sure, especially this is process related, making sure the data is flowing through the system as you'd expect. So this type of mapping is really valuable when you're a data analyst. So you can see your credit records and your customers. Whenever you put in a sales order, it checks the credit record. You approve the sales. You can then release the stock that they have on their order. And then you ship the goods, put a packaging slip on it, put it on a UPS truck.
What I've heard recently meaning like the past 15, 20 years, stores are always talking what they need immediately. So this kind of system, as far as like probably effective in that world.
You're talking about like inventory that they need?
Yeah.
Yeah, they have what's called it's an on-demand inventory.
Yes, right.
What is that? I can't think of it right now. But it's like almost instant inventory where they reach out to their vendors and they can drop ship it. All this means a lot because it helps with the context of data. So like it finally reaches the carrier and you say, what did the customer order and what was their credit record and why was it approved and what did they order and so forth to get it to the carrier. And you can imagine these being multiple tables. So you have a customer table, sales table, inventory table, and carrier. Yeah. And then the process of like billing a customer, sending them an invoice or sales order, and accounts receivable for accounting. How the whole process, how the data gets to accounting, how it will help with the context of data and turning that into information. Okay. So entity relationship diagrams are another high-level diagram. Describes interrelated entities interest with specific domain knowledge, along with the relationships that exist between them. So the entities are like your nouns. So if that seems like Greek, your entities are your nouns. The entities of interest, those are like your business events of the organization. So those would also be, it captures the business events like customer records or order records or so forth. But I like to think of these as the nouns, or the who, what, where, and sometimes why. So who ordered, what did they order, where did they order it from, or who, and then who's the vendor that supplies it. And then potentially tracing that process and saying why was like that person approved for that order. What was their like credit limit and why did that happen? So attributes are the adjectives. They support the decision making. Those are the fields that describe the entities within the table. Then relationships are the key business entities upon which transactions are executed, the dimensions which the analysis is conducted. So the key business entities. So a lot of words there again, but essentially this would be things like a business entity, the two nouns, how are customers and orders connected, or how maybe it's more than one relationship, maybe it's a multiple relationship. How are customers connected with credit records? It connected with then how do their products ship, and then who do they ship with? So maybe like multi-relational, if you think about it, like multiple steps within a diagram that you connect. That'd be like multiple tables that you join. Okay. So something important to note about entity relationship diagrams. Let's see if I can make this full screen to make this a little bit, or close to full screen to make this a little bit more legible. And this is a little bit hard to see.
Yeah, but I can see it here.
Do you see it here? Yeah. So there are two things when noting when you're looking at the relationships of entities in an entity relationship diagram. And you can think of these as tables. So your most common will be your binary relationship. This is the entities with two different entity types related directly to each other. But you also have other examples of this. You have a tertiary relationship. So like this may be your customer, this might be your credit table, and then this would be your shipping or packing table or whatever it might be, your order table. These are all three relate to each other in this relationship. Oftentimes, this table will have a key here, and this table will have a key here. There's also a urinary relationship where one entity is related to the same entity type. So the common example for this is like the manager-employee relationship, where you have an employees table. So you have an employee with a manager, and that manager is also an employee. So that manager is then a key to the same table and keeps following this relationship all the way up the chain to the president of the company. Not very common, but that's probably the most common example. And then the other one is your cardinality constraints, your relationships. So this is where we're talking about your one-to-one or one-to-many relationships. And just to recap that, your one-to-one relationship is where one record in one entity or table matches or is related to exactly one record or entity or row within another table. So then you have one to many or many to ones. Those are the same thing, but it'd be like a one to many would be like one customer to many orders, or vice versa. And then you could have a many to many relationship. So those relationships get huge. The one that I can think of from my example is I used to work in cell phone accessories. So you'd have a whole bunch of phones that are related to a whole bunch of little different products, like charging cords. Say the charging cords can go to many phones, and many phones can go to many charging cords. And there's like beyond the number of relationships that you'd even believe, especially for generic items to phones. But maybe a phone to phone specific items would be like one phone to many items that are specific to that phone. Those are important to capture because those will usually be your primary keys or your foreign keys and the relationships between those tables.
Something like if you had like glasses, and you have like black glasses, brown glasses, things like that, and so there's like many different colors, but is that how would you do something like that?
That'd almost be a many to many, so you do like lab model of glasses or item, like a certain type of glasses under a model. So I have Shaquille O'Neal glasses. That's probably like a certain guy model of it. And then there are like a number of colors that it could come in. It's probably like a many to many relationship.
And would you use that, would that color table be like a thing?
Yeah. You'd have a color table, and then the color would have an ID to the glasses. And the color ID would be a foreign key to the color table because it's not directly describing the glasses, like that relationship, like that distinct relationship in that table, more of a secondary key.
And then the foreign key would, like, if there were like a foreign key, there was like, Mark Jacobs, and there was like, Ray-Ban, and there was Shaquille O'Neal, and then each of those glasses had like different models. The foreign key in the color table would go to
Primary key in the color table. So color table would have like blue, red, orange. So those would be all distinct, would relate to a foreign key in another table.
So then with the Mark Jacob table types, you do like one table?
Yeah. Yeah, you can start decomposing it and breaking it down, and we'll talk about that in one of the forms also. So you could have your glasses, you could have model and vendor and color, and those could all be different tables. And modeling those efficiently. So one other thing I want to mention other than column or how it would be depends on the requirements, I guess, in the system and everything, and gathering this type of information about it and then designing the database for it. There's some considerations, especially on the physical level, when you start to talk to tech teams about how to design it.
They would go and they would see like a model and it would be a brand, like Mark Jacob, Master Church.
Yeah. And it all comes together in displays in their system. Yeah.
The color is not important. The color is like it's really secondary. They're going to go to the brand type and then the model type first.
Yeah.
And that all matters in like how you
Then customize the color, and then they hit buy, and then you record that transaction. And you connect those tables. But the other one is, I want to mention, other than the like one-to-many or one-to-one relationships, there are also optional many or mandatory one or many. So an optional record is like a customer, could be a new customer without any invoices yet. So it'd be like an optional, like one-to-many. So an optional one-to-one. Oh, maybe somebody hasn't filled out their birth date yet. Or I don't know about that. Let's see. An optional one-to-one. So if I'm thinking of a customer, and maybe they can have only one location, like home location. And maybe they haven't decided on their home location yet. It's like not required. Then it could be an optional one-to-one. But the other ones in reverse are optional ones or mandatory ones and mandatory minis. So maybe for a customer to exist in a system, they have to have an invoice. So that'd be like a mandatory mini. They could have many invoices, but to be registered in their system, they've had to make a purchase. And a mandatory one is then maybe the customer does have to have a home location, or else they can't sign up in the system. The system will stop them from doing that, and the database design stops them from doing that. And these actually have examples, so I didn't have to make up my own, but say, so each order, so mandatory one must be placed by one and only one customer. So it's the reverse of it. So if you have a single order, that one order can only be placed by one customer. It has to be placed by a customer, or it can't be an order. And like an optional one would be each order, just that order itself, may be transacted by 0 or 1 employee. Maybe there is an order for some reason that's not transacted by an employee. Maybe it's a customer instead. All right. Got to keep moving. So ERD example of business rules. So I worked on a project with one of my friends when I did the degree program at Creighton and trying to gather requirements for a mobile app that he's creating. So it was this mobile app that allowed repair shops to be able to sign up customers, capture work orders, and then pictures of the repairs that were made. It's like repair trackers, so being able to do those over time, and then track it through mobile app. So then you start asking them questions like, can multiple vendors have relationships with multiple owners, or potentially no owners at all? So you could have a vendor register in a system, so think of that as a repair shop, and they could have relationships with, relationship is like a verb. So that's how vendors would be connected to owners. And they could have multiple car owners or none and no owners at all. So that makes sense. Maybe they're a brand new vendor and they don't have any owners at all yet. Then you do all of these in reverse. So you say multiple owners can have relationships with multiple vendors or none at all. Maybe it's owner car that hasn't gone to one of the shops yet. And then you keep doing this for vendors and services. Like a service record must be attributed to only one business. That's like a mandatory one. And then service records, an invoice may contain many repair images or no repair images at all. An owner can approve multiple service records or no service records at all, and so forth. And then a repair subject would be like the vehicle or boat or whatever that subject is. can have multiple service record, but must have at least one service record to be in the system. And then you could run campaigns and everything through it. So with all of that work, this is the ERD that we captured from it with the optional one in many relationships. So you even have like a tertiary relationship here between the invoice, repair, the image, and the service. So the idea of this whole thing was you can capture a record of your vehicle's repairs, and then you could track it over time, over multiple repairs and shops and services and vendors and stuff like that. And your repair subject would be like your vehicle, and you have a QR code in your vehicle. You probably hate me for telling everyone this, but it describes the whole ERD process and how we captured it. And what's that? Oh no, my friend would hate me for telling everyone about this. But the idea is just that's how we capture it. And you see these little diagrams here. So a single campaign could be attached to multiple business campaigns. So a vendor could run multiple business campaigns. In a campaign, one of those could be attached to multiple business campaigns that a vendor runs. So it really starts to define like how a system works and the relationships and how you define these tables. So you start to see some of the fields here also. And relational database modeling, that's the second level. You start to take that down to where you're defining primary keys and foreign keys, potentially like on relationship. You have a relationship ID with a vendor and owner, or foreign keys to the primary keys of those tables. And you start drawing all these lines and the data types that you need to capture for each one. And then this is usually where you start to generate data if it's a new system, you start to generate data where you use existing data, populate these tables, and start to see if the whole system works and if all your relationships are right. So there's a whole lot of testing and then implementation and then testing that happens. So this ends up going to be your relational model, and then you create a physical model. We did all of that and implemented this and showed the flow of data through an interface. Never made it to mobile app stage, but that was its own creature. But this is a transaction processing database, so it's meant to capture those transactions on cell phone. Okay, that's how OLTP works. So OLAP, dimensional data modeling, there are oftentimes a couple of ways that you can do this. So this is where you're taking the transactional data that's all normalized and stored in those tables, and you're transforming it into your fact tables and your dimension tables, so your business relevant entities and rules. And then your fact tables are things like your prices and your quantities. And you notice how this fact table has a whole bunch of keys so that you can connect it to a dimension. And then you can quickly answer questions like the store in Omaha, Nebraska with this address, what was their total quantity sold of not much of a fashion guy, Nike shoes by a certain employee on the 12th month of 2024. So it becomes very much like straightforward once you organize data into this type of structure to do this for analytical purposes, and they do it over time. This may be hard to do in a system like this because you'll have to figure out all the relationships and connect multiple tables and things like that. And sometimes the business rules aren't already in that system. You end up putting them in these tables in OLAP systems. So business rules would be like certain product. Let's do a product category. It may not be captured in the system, but the marketing team may consider a certain product to be like a certain type, but it doesn't do it within the system. Say this certain type, it doesn't do it within the system, but it's the way the marketing teams use the data. So this could be like product type system and then product type marketing. Then you capture that rule within the product dimension instead of having to recreate it with every query. There are two different ways you can design these tables. So oftentimes you're going to normalize all your data in transactional data, and then you denormalize it into these tables for analytical purposes. So Snowflake is the more normalized tables where you have these relationships broken down with minimal number of fields in each table. The advantage of that is data integrity, space, and all the considerations that go along with normalization, efficiency, data integrity with updates and things like that. Problem is it becomes more complicated to query. You have to maybe join through multiple tables to get through what you need. Whereas the star schema, it's simple to model and understand, but there's more chance that you may update something incorrectly, especially within your dimensions. Like an employee, maybe you get duplicate records. Maybe they change their last name and it basically is like the same employee. Or, yeah, but they change their last name. Or some error in updating values, like we saw in class 3. We were aware of in class 3 being dangerous. But almost always you see this star schema. This is the way people do it, even if these tables are somewhat denormalized. They always have primary keys on them at the very least. And it's really easy to write queries on these type of tables and for analysts to understand. Okay. So I wanted to introduce that because if you ever work in a data warehouse environment, if you're fortunate enough to do that, fortunately, my first job experience so all the data was just available there for me. And I could easily query things and produce reports and stuff like that. It helps a ton with efficiency, so you don't have to go into these systems and figure out all this stuff. It's translated the way people want to see it, and analysts use it. Okay. So last topic here is normal forms. So normal forms are the standard rules for structuring a database to reduce redundancy and data integrity. A couple of times I've talked about normalization. This is what I mean by normalization. So at the very least, early, I talked about having a primary key that distinctly defines all of the records in a table. That would be your first normal form. That's like the standard for relational databases. And then there are a couple ways that you can decompose these that improves redundancy. The chance of redundancy increases data integrity. So they also serve to minimize space costs and error costs. And then the reverse of these normal forms, denormalization involves selectively increasing redundancy to improve speed performance and reduce query complexity. So sometimes within the database, when you're implementing it, you decide to not go all the way down to this form because there are considerations as far as performance in the system. So it's always a balance, and then working with your tech teams for that balance. Okay, so let's see what these are all about, but there's just going to be this saying that every non-prime key attribute must provide a fact about the key, the whole key, and nothing but a key. This isn't going to mean a whole lot to you at first, but I have some notes along the way on each one of these slides that'll kind of help you out with it. But basically, it's like if it's not a part of the key, it has to imply the key in these different forms. So it has to be related directly to those keys. Okay, so there's a whole ton of database theory behind this. I'm just going to cover first and second normal forms because it's all you really need as a data analyst. Third normal form gets complicated, and then there are a bunch of normal forms past that are really hard to explain. I just want to explain the concept of first normal form, which is just like the requirements for a table in a relational database, and then second normal form as a way to decompose it further to avoid redundancy. Okay. So first normal form. So every non-key column in the table must be dependent on the key. So what this is saying is for this table, we have a Microsoft table and stock prices for Microsoft, that all of these columns, Microsoft, Redmond, Washington, and the price, they must be dependent on either symbol or the date. So if you have the symbol Microsoft, company is dependent on Microsoft. The headquarters of Richmond is dependent on Microsoft, and the same for Oracle. And then the stock price or the closing stock price is dependent on the date. So it's also a fancy way of saying each one of these records has to have unique information about each one of these keys or be distinct. Okay, so there are other rules to this. So each attribute must have each attribute, the column value must be a single value only. So what was I saying there? Let me skip that one and we'll come back to it. So all values for a given attribute must be of the same type. So this one's more straightforward. So you can't have a column with variable characters and then numbers in it. They'll have to be of the same type. And that's how we defined a table first. Like their variable character 200 strings or character 5, or this would be a decimal or this would be a date. You can't have a mix of data types in a column. Okay. Each column name must be unique. If you try to define a table with company and another one is company, and won't let you do it. The order of the attributes is insignificant. So no matter what order these are in, if you query it, it'll always provide you the same information. Because if you think if company is over here and you write a query, it's going to give you the same information. No two tuples in a rows in a relation can be identical. That's the requirement of being distinct. And then the order of the tuples is insignificant. So the order of the rows that this is in doesn't matter. So if this row was first, 9.9 was above 9.7, and you summarized all the prices from 9.9 to 9.7, you get the same result, no matter which order the records are in. So going back to that first one, each column value must be a single value only. I was trying to.
It's company, it's symbol, it's location, it's date, it's price.
Each column value must be a single value. Okay. So you can't have more than one value in headquarters. So you can't have Redmond, Washington, and Red Shores. It's weird because, I had to remember because you can't do that within a database. But if you have Microsoft, the only value can be Redmond. it can't be Redmond and Redwood Shores. That key, that unique value has to relate in first normal form to exactly one non-key attribute.
So what does it mean by first normal form? Like what is a form? Or does it just mean like it's a form like as in shape?
Normal forms. So what does it mean to be a normal form?
Yeah.
It's like the standard for structuring database to reduce integrity. So first normal form is like what relational databases are all about, is like it has to have a unique key to uniquely define these records to be able to relate it effectively to other database tables and not have some of these other things. It's like the rules that it has to be like an effective relational database table. And I'd say first normal form is like the baseline for that. And that's what you do when you create a new table. It's like you define the primary key in the columns, and then you insert data and things like that. And you come up with a table like this, where the symbol and date, or whatever your example might be, that follows these rules.
So that is like a table, but is that like just one table, or could that be like what you just showed in the picture? Could that be like multiple tables creating that picture?
Multiple tables creating this one?
Yeah. Or could it be like a table
So joining two tables together. Yeah, well, actually, let's go ahead. You'll see this in a second, how you could do that. You could have two tables that create this result set. Yep. Okay. So Celeste, what I think you're probably referring to here is second normal form. This is like this table decomposed into two smaller parts. And so you had a company table and a stock prices table.
Yes.
And then you could join those two tables to make this table.
Yes, that's right.
So second normal form, so what you have is every non-key column, anything that's not in a key, should depend on the primary key, not just part of it. So the entire key itself. So in this first example, company depends on symbol, but not date. And then closing price depends on date, and symbol, but the company does not. So what you can do is decompose these into two different parts. So you have the key. The whole key here would be symbol. The whole key here would be symbol and date on this stock price table. And all the non-key elements depend on that only. So it breaks these down into two simpler tables.
If you have a third normal form, does it get broken down further?
Yeah. And I have an example of that. I don't cover it anymore. I put it in the appendix. So it would show you how this table is even broken down farther into two tables.
Why would you do that this hypothetically?
Because it helps with updating values inside the table. It reduces space because you have all these smaller tables and you don't have this one huge table. And then two, when you go to update values, you don't have to update a value like 100 times in the database. You just have to, if you have it all the way decomposed, you just have to update it once.
And so some companies do that, and some companies don't. It's just depends on.
Yeah, honestly, not that many people do this. They say that you're supposed to, but I've looked under the cover of these things. Well, it's like all like best practice, right? But in reality, developers don't really implement things like this. That's why they don't want you messing around with things usually. For good systems, yeah. For nice, clean systems. That's the idea behind the project that we did.
Right.
Is that I have to remember if we decompose this, probably like second normal form. I don't know about, he did with like third normal form with this like relationship table in between vendor and owner. Like you start capturing all of it and then you decompose it into its parts. But we'll do an exercise to see this too. The Sequila database is designed with those principles in mind. And we'll do an exercise on it. So the second normal form is like all of its non-key attributes are dependent on all of the key. As opposed to first normal form, where company was only dependent on symbol and not date. Maybe like, this is always the hardest part for me in the class to explain, but second and first normal form. Show you. No, this is the first time we talk about it. This is just talking about these normal forms. It's kind of different from. It's really database theory, but like these are relations between the fields. And I wouldn't worry about it too much. It's like, if you took like a university class, that's what it is. Only the idea that you should have your tables when you design them in first normal form, and then you can break them down into various decomposed states to simplify space and less redundancy when you update. You as a data analyst won't have to do it very much at all, really. But as part of database design, it's good to know these things and how developers to do this and ideally do that in their systems. Yeah, and like a database architect and administrator would work together on it. It is part of the physical implementation of the database. And then you would take all these and then you'd create those tables into an analytical model. And basically the only thing that matters there is first normal form. Okay. So what did we cover in this class? We covered a lot. So transactional versus analytical processing, database modeling techniques. So first one's capturing transactions from a system versus using it for analytical purposes. Database modeling techniques. So these two, entity relationship and data flow diagrams are the highest level. And then relational database modeling starts to get into your logical and physical implementations, like how you actually do it in SQL. Yep. Yeah, I was just adding that since I talked about data flow diagrams also. Normal forms, just learned about that first, second. There's a third normal form. And then there are all sorts of normal forms above that. They get really theoretical and not that practical. And online analytical process with the dimensional data modeling, how you might see it in an organization with a data warehouse environment for analysts to be able to produce consistent results with the same business rules over time. That's translated from transactional data. Okay. Additional resources. I put diagram software on here. In the past, we drew diagrams of these. We did a project and we do draw diagrams with diagrams.net. That's my favorite. Still is to this day. You can go out and there are all sorts of different types of diagrams that you can do, including all the ones that we've learned tonight. I still call it Draw.io, but it's been diagrams.net for a long time. It's free, which is beautiful. Probably better than Visio anyway. Microsoft's product. Ooh. So if I create a new diagram, they're like these nice fancy business things that you can do. But if you do engineering, you can do like system diagrams. These are more like electrical diagrams. UML is like if you're doing software, wireframes for mobile apps. But where's the database? In here, business. If I just use search and I do entity relationship diagram, you can just create an entity relationship diagram right in diagrams.net. And then you see it's the start of the entity relationship diagram. And I would argue this is almost like at the logical layer where you start doing primary keys and then data types before you implement it at the SQL level. But still, all these different ones exist, software ones exist. And I still do this a lot to map processes and things like that. Actually doing that for a client to process document for mapping the process I created for updating their data in Python. Of course, a new favorite, you can always put this into AI. I created an ERD diagram for the Sequila database here somewhere, or I can just type it in. I'll just oh, nope, I did. Or no, I didn't. So I could do something as simple as create an ERD diagram for the MySQL Sequila database. This has become my new favorite. I did this before class. I just can't find it. It draws it all out itself. Does analysis. It takes a moment because it does this code like behind the scenes. I had actually thought about that project that I did for the repair tracker, putting my code in ERD diagrams and see if it could create me a mobile app or how far I'd get. Call it like vibe coding now, is that you just have a thought and you just start typing it and there's your code. It's not, I feel like that's oversimplified. It's not that good yet, but there's your entity relationship diagram. Connected to films connected to language. Then you have your one-to-many required or optional. Then it shows you the tables, which are the entities, your attributes, which are the fields, and your relationships, your primary keys and foreign keys, so forth. Just does it for you. I bet you could feed it if you gathered requirements, like I did with that project. If you gathered like this, that's a class project. If you just went and started typing these things, class 6. If you did something like this, got requirements like this, that it would just create an ERD diagram out of it. So I should paste all, I'm calling these business rules. So that's basically what they are. Where's the other part of that? I haven't even tried this, so I just thought of it. It's going to create the same one I did. I don't know. Oops. I hit enter by accident. Oh, well. I'm going to add these to it. It should work because this defines these unique relationships. You don't have to have the rest of it. We'll add these to it. This is why I say we should use this type of stuff. This must have taken us a while, the business rules, but creating that diagram must have taken us like 20 hours. Where now you can just do this. Now we'll add these. But yeah, like 2 minutes. And you can just add these business rules to it. And you could probably also feed this SQL code, like in your Sequila database. You have to get like all the database code, but then it just generate this diagram for you. But of course you could go out to the internet and do this, and look at that ERD, but I wanted to show you the power of it. Like I just generated it by asking. Just by asking, say, generate an ERD of this MySQL Sequila database. Because it's like a standard database that people use for learning. Oh man, I'm putting it to work here. There we go. How's that compare to mine? I like my formatting better. So like campaign. Can I move these around? No, not really. Campaign would be attached to like owner and vendor related to them. I don't know. I can't really tell when this thing's not dynamic either. That's the only bad thing is like it might not. This one might not actually go to campaign. That might just be drawing a line through it. I can't. Yeah, it's not perfect, but I had it easier to read at least.
Well, it was very well thought out. Yours was.
Yeah.
You can find out if see if Code makes mistakes.
I bet they did. Somewhere in there, I made mistakes in this one, defining some of these relationships. Professor gave us an A, so said it was good. It can be a little subjective too, but you write them out like that to really define it. Understanding all this just helps you as a data analyst. All right. So we finally come to the end of class. So there's a 1 on third normal form if you want to know more about it. Decomposing that second normal form table into third normal form. That's about as far as any developer goes with transactional databases. The rest of it's really theory. And then a heads up for class 7, what we're going to do. We're going to learn some advanced features, SQL features. What's the difference between what we've learned in procedural SQL? You can create your own functions and routines and things like that. We'll learn how to do that. And things called temporary tables and table expressions. So we've been writing single queries or even things with subqueries in it. Temporary tables are a way to store data temporarily. You can break a query into multiple parts and put data in a temporary table and then use that within a query. Table expressions are more like stacking a bunch of queries one by one. So you have one and then you use it in the next one and then you use it in the next one. Sometimes these both can be easier than doing multiple nested subqueries. So we're going to learn those things to finish it off. The lecture is fairly short on Wednesday, so hopefully it gives us a lot of time to work on class projects or homework. Okay. Given that, we have about a little over 30 minutes. I'm going to give everyone a 5-minute break. We went through a lot, and then we'll cover the ERD of the Sequela schema, identifying that. So in your homework, so in this final homework I have, it's more about the table that you created, the games, and then identifying the relationships and entities and attributes in them. You've already done that for the most part, but I'm just thinking about how to put it all together now. But this exercise will help you, should help you with that once I release that final part of the homework. Give everyone 5 minutes and we'll cover this exercise going through this ERD diagram. Or this is actually the physical model diagram. Or not the physical, the logical model with the tables and the names. And it'd be logical model with data types. So be back in 5 minutes. 8:31, we'll start. See you in a little bit. A few minutes. home stretch. Bringing everyone home. Wait just a second while I bring it up. So it's repeating what Celeste asked me, is that we'll sign the final exam on Wednesday. That'll be due the following Monday. So Wednesday is the 2nd. That will be due by the 7th. 6th, yep. 7th would be Monday. And the last part of the project, the final homework and last part of the project, I'll try to get it out to you tomorrow, or it'll probably be Wednesday. That will be due the following Friday, the 11th. So I can review and grade it before the next class, before I teach data engineering class. If you have any questions about that, please let me know. And we'll do these exercises. Yeah, in the meantime, the next couple days still gives you a chance to get caught up on the other homeworks. And then a little bit of time before, actually almost 2 weeks before everything's due. So still time to get through it, and always here to help. Okay. Class project, or not class project, exercises. So here's the Sequila database. I'm familiar with it from the homeworks. Here is what the logical diagram looks like. And that's actually the answer to the first question is, what type of database model is this snapshot? So if you went up here, what's that?
Can you give us this? Is this in our PowerPoint?
Yeah, should be. Is it not?
Yeah, it just looks like that. It has blue, but is that? No, it doesn't look like that.
Can I see yours real quick, Celeste? Oh, that's a class project.
What are you showing?
The lecture 6, exercise for lecture 6.
Lecture 6, okay.
Yeah. So still doing lecture 6, just doing the exercises at the end of class. Got to them with 30 minutes left today. This will actually be fairly fast too. So in all of this, we haven't wrote any code, but I can show you a trick to being able to see this type of diagram. So I think this was asked some point in class, but if you could see a diagram of the database, but we're going to go ahead and I'm going to go ahead and show you how to do that. So if you go up to database in MySQL Workbench and you do reverse engineer, you'll follow this reverse engineer database. So what's it's going to do, I kind of talked about it. If you don't have these diagrams, you basically have to reverse engineer the database and the relationships and stuff like that. Fortunately, MySQL Workbench does that for you as a tool built in. So if I connect to the database, put in my password. If I click on the Sequila database, select schemas to reverse engineer. Go ahead and it's working on doing that. Retrieval completed successfully. Then select object. So I don't have to do the view. Well, we could do the views. We'll take these other objects out. We'll learn about those in the advanced SQL class on Wednesday. Execute. So we'll just do views and tables. Okay. Operation successfully completed. And this one has a really nice editor for the physical model or for the logical model. So you have all the tables, data types. You even have indices, which we don't cover in this. Basically, it's a way to index the table to make queries faster. I hardly ever do it unless you have a table so big that it's running super inefficiently. And then it's usually not even an issue either. But it is if you're talking about a system, transaction processing system, and needing to be able to do things in milliseconds instead of seconds. I was trying to see what was up there at the top, but you can navigate around these, see the relationships. I think these are views. Create algorithm. Yeah, these are views. These yellow boxes are views inside of here. And then you could see what tables they're connected to through the dotted lines, I believe. Or maybe these are just randomly put in here and not through the dotted lines. Oh, you know what this is? So these are just kind of put here between the table relationships, but the dotted lines here are your foreign keys and the solid lines are your primary keys. And you can see the relationship on each one of these two. So you can see that it's mandatory many. From one to mandatory many, language has to go to a film category. So it's saying if the language is in the database, a single one, it's mandatory that it goes to either one or many film categories. So you can reverse engineer all that and scroll around. That's kind of what I was looking. That was what I was looking for. I was trying to scroll myself. And then your catalog tree. Yep. Save model as. You can import it as a MySQL Workbench model. I think that you can export this as an image. Database. If I got option in here, I haven't done it in a little while. Database tools. Where you can save this somehow other way as an image. I'll try to figure that out for you. I'm pretty sure you can export this as an image. No. But I am only a Claude question away from knowing. Used to be Google, but Google messed up. Not being where they should be. They have all the data and technology for it. Let's see. How do I export a... Yeah, it indexes all that information. And it's just really what generative AI is a summary of everything out on the internet, or as much as possible. And then logic that solves your problem. Okay. It looks at all the articles and all that information and it interprets it, your question, and then finds the best match. But it's using algorithms instead of Google's proprietary indexing and search. I don't even bother looking things up anymore. Maybe he'll tell me he can't. I was just dreaming it. I'm hallucinating it. That'd be funny for AI to tell me I'm hallucinating it. Okay, and they don't always give you the right directions either. Okay, database, select the schema, complete the wizard. Once the diagram is displayed, select file export. Oh, there we go. Export as a PNG. I should have looked at it in retrospect, but I'm like, view, save. There we go. That's why it's my new best friend. Okay, let's go through these exercises. Sequela database. I don't know how much time it's saved me already.
Yeah,
I'm
2 minutes versus 20 hours.
I bet it's already saved me like 1,000 hours doing stuff. Yeah, and then knowing when that doesn't seem like the right answer, or redirecting it to what you need. Okay. So I created a walkthrough for this thing. So what type of database model is in this snapshot? So it's logical. It's the next step away from the physical, which is the actual SQL implementation. This is database independent. So no matter what relational database system you implement this on, say this model will be your guide for whatever code you need to write. So when you do the physical implementation, you have to write it specific to MySQL or Oracle or Microsoft SQL Server or whatever it might be. And then all the considerations that go on underneath the scenes there with your database architects and administrators. That would be your physical implementation. This is just one step above that. It defines your relationships, your entities and attributes, your nouns, all of your nouns, your staff, payment, rental, inventory, all your adjectives under each. Better one would be, let's see, how about staff, like first name, last name, address, picture, email, all the stuff that describes staff or describes rental or whatever it may be, customer. And then your relationships between each table. So like between film, there's exactly one film to mini inventory, which would make sense. You probably have more like a copy, or it's optional mini. So you have exactly one film, and it could have 0 to many film of that film in the inventory, which makes sense. That's what that relationship tells you. Okay. So question 3 is film in first normal form. So let me get these answers. A good answer for you. It is in first normal form, but let me tell you why here in a second. So if you start thinking about things like primary key being defined, each row is uniquely defined by the key, or like your key elements define your primary key, that it does that. All of the columns have their own name. There are no duplicates. Sometimes you'd have to dive a little bit deeper into the data to know for sure, but the record, the order of the records wouldn't matter in film. So all these attribute, let's see, and then all the values in these columns are all of the same type. That's one thing that we learned. You don't have characters and then entitle characters and then number type values in it. So they're all tightly typed. And all of those attributes, like we saw, they contain a single value. So you'd have to look in the database table like we did before to see each row. Each one of these has exactly one value per record instead of multiple. So this is why relational databases are all about, is storing data that way. So if you needed to have like multiple values for a single row, you're probably looking at a different data type, like a JSON file or some other alternative type. It wouldn't be a relational database. But, and sometimes once in a while there's a need for that. But as far as relational databases are concerned, you'll always meet those criteria. Okay. So the next one is that, can you name a relationship that is at least second normal form? So there's one of these relationships here, rental. You know that it's in second normal form. Well, first of all, it's in first normal form. That's a requirement for it to be in second normal form, for all the reasons that we talked about, film being in first normal form. Okay. So the second one is that all the non-key elements. So that would be the rental date and return date. Rental date and return date. So the foreign keys are part of the key here. So rental date and return date and last updated all are dependent on the rental ID. So that rental, when the rental took place, would be the rental, or that rental ID. So you'd have rental IDs like 1 through 1 million, inventory, and customer ID. Say the rental date is dependent on all of those. And so is the return date and the last updated and staff ID. All right. So then there are no partial dependencies. So all these are related exactly to that key that we defined. So rental ID, inventory, customer, staff ID. So all those are needed to determine the rental date, return date, last update. And sometimes this is hard to see too, because it takes looking at the data inside of the table to really understand that. Especially, so think about it as the last update. Last update is dependent on that rental ID, what ID it is in inventory, who rented it, and that staff member who did it. And that each one of those rental records will be defined, the last update date will be defined by that, and the return date and the rental date. Okay. Let's see. So that's 4 and then 5. Find the following relationships in the schema. So we have mandatory 1 to optional many and optional 1 to optional many. So you can find things like this. So a mandatory 1 to optional, that would be optional many. You can tell by these lines and the symbols that are on them. So a mandatory 1 to optional many would be language to film. Optional 1, let's see, optional 1 to optional many, it'd be this relationship right here. This one? From language to film. Yep, the language entity or table to their film entity and table. So what this is saying is that one language, wait, that's this one right here. Sorry, I pointed to the wrong one. That's optional 1. I don't know why it has a 2 line, or I think these are the directions of the relationship. It should be this one to this one. Language to film, and it's the mandatory 1 to optional many. So what this is saying is one language must exist for films to reference it, and a language may have 0 or more films that it is attached to. So basically, every film must have a language, but not every language needs a film. And that's that relationship. And this one is, these are hard. So language would be, must have one language defined, and it can go to optionally many films. What's that?
So mandatory 1 to optional many, be language to film, optional 1 to optional many, to be language to film too?
Yeah. So that's saying like for every film, optional many, language may have 0 or more films. I don't know what this other relationship is here, right here. I don't know why there are 2 of them there. It should be bidirectional. Like there's another one here too. Okay. Anyway, let's go on to the next example B here. So optional 1 to optional many. So let's do customer to rental. So that should be this one. So this would be a 1. That's an optional 1 to many. Customer. So this is a mandatory 1 to optional many. Maybe I have these backwards. So there must be one, a customer may exist without ever renting any movie. So this is mandatory 1. So the customer must have to exist. And they could rent 0 or many. So it's an optional many. So a customer may exist without ever having made a rental. And then the opposite is, you would say a rental cannot exist without a customer, without any customers renting it. But the customer may have 0 or more rentals. So that's the mandatory 1 to optional many. So it goes both directions. So I'll just restate that. So a customer can have optionally many rentals. So it could have 0 or many rentals in the system. And then if you trace that the other way, it says a rental cannot exist without having any customers. Sometimes these can be a little challenging to interpret.
They're very challenging.
Sometimes it's easier to like see the data, but this will help you with like once you start joining these tables, why you get those result sets. Like if you do a single customer, and you join it to the rental table, maybe you'll end up not having any rentals for the customer because the customer can have 0 or many rentals. So I'd probably use it for that as much and then go to the data and then like understand the relationship that way. So let's try to do another one. Let's try to do like an optional one to optional many and interpret it. Here's an optional one to optional many. So payment and rental. Optional one to optional many. So what is this saying? So for rentals, it's optional if the rental exists, which may go to, so rental ID would be for a movie. It's optional that a rental is on inventory. So there may be 0 or many rentals on an inventory, a customer, and staff ID combination. Okay. So on that primary key, optionally many or optionally one to a payment, there may be optionally many payments for that rental. So I'm guessing you can pay for it in multiple ways, or you could do multiple rentals with multiple. Oh, it says one rental with multiple payments. Maybe you can get late fees too on it, and then you'd have another payment. Let's see if I can type in Claude what it thinks the interpretation of this is. Optional 1, 2, optional many. Relationship between rental and payments. Personally, I'm a data guy, and I'd like look at this and query it and say, oh, that's what that means. Okay, it says a rental record may or may not have an associated payment to it. Let's see. May or may not have associated payments. This might occur in several business scenarios. A rental might be complimentary. Maybe you rented it and no payment was needed. A payment might be waived for a loyal customer. Payment might be pending or processed separately. So you could have a rental without any payments.
That could be the same for anything then, right? In any scenario, like maybe the person paid or not. Right?
Yeah, optionally they paid or did not pay. So it says multiple payments can be associated with a single rental. This is what I was having a hard time with. A single rental optionally. This could happen if a customer makes partial payments over time. A deposit or final payment are recorded separately, like a late fee, or refund or adjustment is processed as a separate payment record. So there's a lot that can go into these systems. Imagine a system that has really hundreds of tables. And it it definitely happens.
About that, and I'm thinking like, yeah, what about in real life? You know, like hypothetically, yeah, but like.
And it says all of this is implemented through rental ID. Yeah.
But, I don't know, like having different, I guess you could just
And it says all this is implemented through rental ID.
Okay. Okay. But there's no, okay. Okay.
It says this type of relationship provides flexibility in database design to accommodate various business scenarios
Okay.
with rentals. What would be interesting is to take a diet and to import like a big ERD for some existing system and see if it could interpret it. I don't know how I would do that without data. Maybe it could. But yeah.
If rental ID is whatever, then
Yep. So that's it for this class. Hopefully that was a little helpful, but it can be complicated. The key is understanding entities,
helps for you going through it because I know that is very difficult.
attributes, the relationships, which are the lines, the type of relationships, and the significance behind all of it is all you have to all put all of that together to really interpret the data.
Yeah.
Like you'd have to know that some payments are like they either don't happen or some of them are adjustments and stuff like that. It helps with the context of the data, turning it into information. Well, that's it for class today.
The database design, because if you're thinking of there, these circumstances where you count the person.
Yep. You can let it.
Discounts, like different price.
Yeah, discounts.
So
yeah, and all these things or rules or considerations like just go into the design of the database. That's why these things in big companies can literally take years to do and to implement.
We had a database in the company where I worked. It took a long time, and then the testing of it took a long time too.
Yeah, and then you have to test all of it to make sure it works the way that you wanted.
Does because when humans get their minds in there, they kind of get in labyrinths. But I wonder if Claude does better.
As far as like interpreting this, than humans, I'm sure.
Yeah.
I struggled to interpret it without knowing or seeing the data or like knowing the system that well or seeing it.
This is one of the things I looked at when somebody tried to explain it or something like that.
This one, I'd have a hard time imagining that you could just feed it to like a regular ERD and feed it, and then it would just give you a definition. I guess I have one. I have that repair tracker ERD. And see what it'd do with that.
Ask Claude to define, like with the DRD that's on manufacturer. Ask Claude to define, like what are the all the different types of relationships and
Here, I'm going to do this.
But it has to be one that probably, rather than just an image, it has to be people. You can do images, but like one that's just probably, in text, form define all the relationships.
Okay, we're just going to paste it in here and see what happens. Okay, everyone. Okay, it gives you the obvious entities. They say this is a service business management system, which it is. Relationships. Okay, the system appears to manage a service business where vendors provide services to repair subjects. possibly equipment or properties owned by their owners. That's true. System tracks campaigns, maintains account. It's kind of vague. Yeah, it gives you a quick interpretation. Give a deeper interpretation of the vendor to service relationship. Relationship is labeled provides, indicating that vendors are the entities that deliver the service within the system. One-to-many, meaning a single vendor can provide multiple services, but each service is associated with exactly one vendor. Has important business implications.
Can I ever tell you, like, I don't understand what you mean? Can you clarify it?
It always tries to answer it, even if once in a while it just kind of says, I don't know what you're talking about. I need more information. But even it tries to answer almost everything. Vendor to service. Relationship vendors have specific service capabilities. There's likely specialized in particular types of repair. That's true. Now I just need to see if it'll create. Everybody now has the information needed to create this mobile application. Great. See you, Celeste. All right, everyone. Thanks for hanging out with me here today. Hopefully you learned a lot as far as database design. I feel it's important for a data analyst, which is the focus of this class, in understanding this. And then, like I said a few times tonight, taking data and interpreting it into information by knowing these relationships and these diagrams and taking it from transactional to analytical data. And yeah, Matt, I see your comment. Identical to Draw.io. It is Draw.io, the diagrams.net. They just rebranded like a few years ago. But it's the same thing. I always call it Draw.io. But it's diagrams.net now. See if I can answer any questions in the SQL channel. Wait here a few minutes if anybody has any questions. We had a fan comment. Said, great going. Someone on YouTube watching our video. Happens once in a while. I don't know how people find him live. Must have some type of search algorithm. Okay, and last note for everyone in the class, I'll mention it one more time. Say no quiz over this class or the class on Wednesday, but material will be on the final. I will work to finalize the homework, which completes the class project for lectures 5 through 7 or classes 5 through 7. You won't be responsible for any materials in class 8. because that's just a kind of a bonus lecture. The final exam, we'll hand that out on Wednesday also. That will be due the following Monday. And then the project I'll also hand out this Wednesday, be due the following Friday. Okay. Go ahead and do an outro here. Go to full screen. Okay, make this full screen. Pretty good. All right. So this is Jeremy Bergman, the instructor for Data Manipulation and Management in SQL 101 in Omaha Data Science Academy. This is class 6, database design. So how you structure and model data within transactional databases and analytical databases. The next lecture is on advanced, and final main lecture is on advanced SQL features. This includes ways to take complex queries and break them down into smaller pieces through temporary tables and common table expressions. Talk about the differences between those on Wednesday. We also we'll compare standard versus procedural SQL. Throughout this class, we've learned standard SQL. We'll talk about the advantage of using procedural SQL. It works like a procedural programming language where you can do step-by-step logic instead of just writing SQL queries. There are plenty of advantages to that we'll show. And then other procedural SQL techniques, like how we do it, creating other SQL routines. Those stored procedures I talk about is how you capture procedural SQL. But you can also create your own custom functions out of it, column functions or summary functions, and then database triggers that update values based on other actions in the database, particularly useful in transactional systems. So once again, this is Jeremy Bergman. Thank you, class, and I'll see you on Wednesday.